Hello everyone, my name is Florian Kanitschar and I'm pleased to present you the results of our research on finite-size security proofs for discretely modulated continuous variable quantum key distribution protocols conducted at the Institute for Quantum Computing at the University of Waterloo. While it's my honor to present our work to you, the research behind this poster is the result of common efforts with my collaborators. As the title of our poster suggests, I am presenting a finite-size security proof for the CV-QKD protocols in the finite-size limit. In more detail, I finite-size security proof against i.i.d. collective attacks. Let me start my presentation with a brief introduction. Discretely modulated CV-QKD protocols are a promising candidate for early commercial implementations of quantum key distribution as they rely on laser sources and heterodyne detectors. And both are state-of-the-art infrastructure in nowadays telecommunication networks. So far, various security proofs in the asymptotic limit, so under the assumption that Alice and Bob exchange infinitely many signals, are known, while security proofs in the finite-size regime are still subject to active research. We prove here composable finite-size security against collective i.i.d. attacks, which means that the considered quantum states have tensor product structure. Next, let us talk about the quite general protocol we consider in our analysis. In the first step, Alice prepares one out of NST coherent states alpha, which are discretely distributed in the phase space according to some probability distribution. This state is sent to Bob via a quantum channel, who then performs heterodyne measurement. This procedure is repeated n times. In the next step, Bob randomly selects some rounds and performs a so-called energy test. This test can either pass or fail. If it fails, Alice and Bob abort the protocol and may start afresh. In case the test passes, they proceed with parameter estimation, which again either passes or leads to a restart of the protocol. If both tests were successful, Bob performs a key map, assigning logical values to his measurement results. And this is then followed by classical error correction and private simplification. In the end, Alice and Bob obtain an epsilon secure key. Okay, before we come to the idea of our proof, let us talk about some of the obstacles we face and how we resolve them. Since we deal with coherent states, the relevant Hilbert space is infinite dimensional and Bob's observables are unbounded. We tackle this issue by performing an energy test, which helps us to restrict our considerations to a finite dimensional cutoff space, and then we apply the dimension reduction method, which allows us to rigorously replace our infinite dimensional optimization problem linked to the key rate finding problem with a finite dimensional one. Although we have now bounded Bob's system, Eve's side information is still infinite dimensional. Furthermore, finite size corrections have to be taken into account. And we resolve both tasks by rigorously applying infinite dimensional smooth entropy calculus. So it turned out that the main obstacles are related to Bob's infinite dimensional Hilbert space and Eve's infinite dimensional side information. After performing our energy test, which bounds the weight outside the cutoff space, we can tackle the two problems separately. On the one hand, we establish epsilon security using infinite dimensional smooth entropy calculus, and on the other side, having bounded observables enables us to apply the dimension reduction method. Having both resolved allows us then to use an extended version of our group's numerical security proof framework to finally obtain a lower bound on the finite size secure key rate. Okay, let's now come to our energy test. It enables us to determine the weight of i.i.d. states outside the finite dimensional cutoff space using quadrature measurements. Let us call the number of signals used for testing by kt. Then we pick a weight w, which has to be between 0 and 1, and pick a cutoff number nc, so natural number, and a testing parameter beta, which should be positive. Furthermore, we denote by pi orthogonal the projector onto the complement of our cutoff space. Then, for all rows such that its trace with the projector is greater than the weight, the test fails, except with some small failure probability epsilon et. Having now the energy test in our hands, we can come to the security statement of our proof. Besides the epsilon for the energy test we just introduced, we also have an epsilon for parameter estimation, a smoothing epsilon called epsilon bar, as well as epsilon related to error correction and privacy amplification. Then, if the output of the quantum phase of our objective QKD protocol is i.i.d, the protocol is epsilon secure, given that in case the protocol does not abort, the key rate is smaller than the right-hand side of the inequality we state here. Let me now draw your attention to the last column of our poster, where we illustrate our results. While our security proof works for a quite general class of DM CV-QKD protocols, for illustration purposes we applied it to a 4-state phase-shift-keying protocol, which means the signal states are 4 coherent states which lie on the axis of the phase space with displacement alpha. Every state is prepared with equal probability, so in our case with probability equal to 1/4. And furthermore, we allow Bob to perform post-selection. In the plot which will follow, we present key rates for ideal untrusted detectors, but however our analysis is also capable of including trusted non-ideal detectors. Plots for this situation can be found in the preprint of our publication. Yeah, let's come to the first plot, which displays the secure key rates over the total number of signals sent for different testing ratios. It shows that for low testing ratios, the secure key rate, so if we for example look here at the blue curve, which represents a testing ratio of 2.5%, and then the curve converges to the asymptotic limit, which is here displayed by this black horizontal line, which corresponds to exchanging infinitely many signals. And this is exactly the behavior we would expect from a valid security analysis. In the second plot, we fix the number of signals sent to 10 to the 12 and plot the secure key rates over the achievable transmission distance for a fiber with a loss of 0.2 decibel per kilometer. One can see that for low transmission distances, low testing ratios lead to higher key rates, while it's the opposite for higher distances. Secure finite key rates can be obtained until almost 100 km, here for a testing ratio of about 40%. And we also want to note that secure key rates for practical distances can be obtained also with a lower number of signals, and again, there you can find details in the preprint of our publication. Let me sum up what I presented. We developed a finite-size security proof for discretely modulated CV-QKD protocols against collective i.i.d attacks, and our key rates are tight and converge to the asymptotic limit for large block sizes. We show that secure key rates can be obtained for transmission distances of up to 100 km, which corresponds to about 20 dB loss in state-of-the-art fibers. And this result is an important step towards practical feasibility of CV-QKD with discrete modulation, as we take finite size effects under experimentally viable conditions into account. So thank you very much for your interest in our poster, and in case there are any open questions, I'm very happy to answer them, for example within the frame of the poster session of Qcrypt 2022. For more details, I also can recommend the preprint of our publication available in arXiv. Thank you.